So I'd like to invite Chad Foerster, who has extensive experience in the use of testing and finite elements to guide the design processes. Here you can see a little of his story background. He was the enterprise chief engineer and VP of technology development at Virgin Orbit. He provided extensive expertise across all areas in the company regarding engineering, manufacturing, flight, launch, supply chain, and all that. He was also the chief systems engineer of Virgin Orbit. He was also the chief engineer of Launcher One Evolution, the manager of second stage structures and mechanisms. And prior to that, he worked for the Aerospace Corporation, also developing new launch systems and spacecraft. So with that said, I have had invited Chad to give us his perspectives about the use of finite elements, its limitations, and when can it be useful. So there's a Q&A between you and I and Chad, and you guys can also ask questions if you're okay with asking questions. So Chad, any words before I get started?
Yeah, thanks for the invite. I definitely have seen modeling used in various places, both at Aerospace Corporation prior to my experience at Virgin Galactic and then Virgin Orbit. There's a lot of interesting things, that you can do with it between composites and metallics, and then also, in the kind of local scale and global. And they're all very useful spaces, but yeah, looking forward to the questions that you might have, Bené. So you can lead the witness a little bit here, and let's see where it goes. But
yeah,
it's very interesting, and I highly recommend everyone to take in their career a final element course and really understand the fundamental mathematics behind the derivation, because it really does help kind of get an understanding of what you're doing in the background when you're using pre and post processors like PMAP or others. So go for it, Bené.
Yeah, thank you, Chad. We're gonna start very top level with the first set of questions. Chad, you always tell me there's few kinds of engineers, few type of engineers. Ones are more creative, things like that. Can you tell us a little bit about the kinds of engineers you've encountered when you're in management and the strength and weaknesses you see in how those engineers manifest themselves in these companies?
Yeah, so I've usually tried to stick to like 4 classifications for engineers, and this is really probably more like your primary personality as an engineer. It doesn't mean that you don't have capabilities in the other 3, but you usually have a dominant one, or maybe 2 dominant ones. Maybe you have 2 dominant and 2 non-dominant. And so what I've seen is, you have the fundamental designers, and these people are probably the most looked upon as artists. They're people that are really good at CAD, doing fundamental first principle design, usually very visual people, tactile people, and they will go and just create great designs, but they're not as into the next type, which is an analyst. So analyst is really where you find some of the people that really get into the final modeling code, really blossom and really create a lot of value. But analysts, and just like designers too, you can get trapped. Designers can get trapped by just constantly wanting to change. That's really kind of the artist embodiment in that group. And then an analyst, they can get trapped by just analysis paralysis. They're always wanting to reanalyze, and it's hard to say it's good enough, or it's hard to say that the fidelity is good enough. Right? That's one of the biggest things. Like, oh, I could go deeper. Sometimes you have to call it, put the pencils down. The other 2 types are more they're more kind of person to person interaction types. And so one is what I call the kind of hustler. And so they're always they're actually the people that are usually get involved with testing first, and experimentation, and with designs, and even analysis, and trying to correlate analysis and design. And so those are the people working on the floor and working to manufacture things pretty quickly. And all of these people, including the last type, can be one type of engineer, mechanical engineer, or aerospace engineer, or a propulsion engineer. So the last type is a politician, actually. Some people are really good at understanding a project and where you're getting support from, both monetarily and also people support, and kind of navigating that process and really putting together teams and creating a lot of momentum behind either certain designs or analysis or builds, right? And so there's a political aspect that is important, right? And that's really part of aerospace engineering because it's such a complex field where you have to have 10,000 things go right and one thing goes wrong. You really are relying on a lot of that combined knowledge with the team to really execute on a design or an analysis or a build. And so that's the politician type. So those are the kind of general things. You can see various manifestations of that with other people and how they describe engineers, but all of those types of engineers can be successful, but you really want to make sure you understand your dominant types or your dominant type, and then also your non-dominant, so you can work on all of them, right? And then understand in a project where you're going to fit in, and you might fit in a non-dominant way in a project as a puzzle piece, but that might be the hole that you need to fill. So that's kind of my general advice. And when you're building a team, you want to pair people up that have different dominant strengths, so that you get this kind of combined team that can do everything, and they can even pinch hit for other people in their non-dominant skill sets, but they have a really dominant thing they can bring to the table that is different than other people. So the paired programming approach, where you put two people together, or the people in 4-packs, those are the best teams that I have helped build and been a part of in terms of execution and success. And also failure. I mean, getting to failures and getting through them and being resilient and working to succeed the next time.
Yeah, so Chad, that's excellent. I really appreciate you bringing up the kinds of personalities that can be encountered from the engineering perspective. And with that said, when it comes to finite element analysis and finite element modeling, how does that connect with the kinds of personalities you encounter? I will assume that somebody that has analysis paralysis will create the first model and then delete it and start over and delete it and start over, maybe not even move a finger. Can you kind of connect those to the kind of personalities you've seen?
Yeah, that's interesting. I mean, you can apply that personality type to almost anything. So in FEM, that kind of manifests in a couple different ways. So for designers, what I've seen, the best designers, they end up using FEM and as a cross check of their design. So they're really living more CAD space, and they maybe are working in an environment like NX that has a final modeler in the background in Advanced Sim that is matched to the CAD, that has auto meshing properties set up. And so they're actually doing cross checks on a very similar model and understanding how they can manipulate the CAD while not breaking their final model and running it. That's unique. But a lot of things that the normal designer will just proceed with the design with first principles and then do a final model at the end. And that's actually valid too. And I've seen that work a lot of times. That's pretty efficient. And the worst designer doesn't do final modeling at all. I mean, if you're going to be a good designer, you really want to embody some of the final modeling. Even if you've been doing that design for 20 years. I hired a person that was did a lot of aircraft design, but he never done final modeling. And one of the things we taught him was final modeling, and he really got an appreciation for what he could do with his designs by understanding final modeling. So that's what I see in designers, right? They might wait and do it at the very end, never do it at all, or if the best ones, they somehow link their CAD and link their art basically to that analytical approach. The analysts, you have the deleters like that. That's the constant iterators, right? Rip the page off and crumple it up and throw it in the trash can. That's pretty prevalent. Sometimes that does work though, especially if you're doing smaller, lower fidelity models. The problem is when you get into the higher complexity models, that's really hard to do because you develop these linkages, whether it's super elements or you're developing a very detailed, CLA model without super elements. It's harder to do as you develop the complexity of models. So you really want to understand when you're in that mode and just understand if it's value added or not value added. Paralyzed by modeling, I think also comes into how you refine a model, and how you might split out some like global low fidelity into local high fidelity. Analysts tend to want to go overboard in some of that, and like for instance, if you're in a bolted joint, like you have 8 of this repeated joint, you might only need to do high fidelity in 1, right, instead of doing it in all of them. So there's a aspect to analysts where you have to really be careful about how much you refine a model, and that matters not only for compute time but just your time in doing the meshing. But I do find that analysts, they apply that kind of artistic talent to the mesh, and so they can be some of the best meshers and understand disconnects and nodes and really boundary conditions at dissimilar meshes, and really have fun with that from an analytical perspective, because you're understanding how you're linking in two boundaries. Boundary conditions are everything in biomodeling. So analysts are really good there. Strengths and weaknesses. For the hustlers, it's interesting. They throw a lot of stuff at the wall. I really have found the best way to help those people is have them very directed, in what they're doing with a model, because they're kind of all over the map, right? And they might end up breaking models the quickest, which is sometimes good, so that you can understand really the weaknesses of your final models. But they end up producing garbage results a lot of the times unless they're really directed and taught, because it's not really a dominant trait for them. So there is, again, you can do that type of technique, but usually it's really good more in a learning environment, or you're doing like really small subscale testing. But in the end, you got to produce something that's not garbage. It can't just be a learning tool. It has to be a functional tool. And so that's the biggest thing for hustlers, is to watch out for that. A tendency to just like throw stuff at the wall, and in the end you're like, that result looks, I've got a result, and like you don't know if it's good or not. And then last is the politicians. I guess there's not really a, let's see. Well, I would say those types of people are very thoughtful in how they approach it, and they're really looking at, is there any prior art that can be used, that we can go faster on, right? They're not looking to reinvent the wheel, and that's a really good thing. I mean, you don't need to reinvent the wheel on FEM. You can go and peruse someone else's bulk data file, or peruse their model in, an Abacus pre and post, and really get to know it. It might be really valid, and really you can then focus on results for a different boundary condition, or really increasing the fidelity in a local area. They're not really the crowd that says, not invented here, I got to remake the whole thing. So I would say that's their best strength in that approach. And their weakness, I think, is really not really understanding the fundamentals of what they're producing, in terms of the mathematics and the boundary conditions and all that. So, you really have to dive deep. And if you embody more of that personality, sometimes there's a tendency to kind of stay surface level. And you really can't do that with them if you're the principal analyst. You got to go deep and really do double checks and triple checks of everything, and do some test cases, for your mesh before you apply the more complex loading that might be flight loading or something in a test environment. So that's a long-winded answer, Vinay, but that's how I would dissect those 4 types and how it manifests itself in finite modeling.
That's an excellent perspective. I really appreciate that. There's also the types where a project is given to them and they quickly start accelerating and getting stuff done without having any context. The finite model is created, analysis results produced, and they're meaningless because there's lack of communication. Can you go into the importance of communication across disciplines, across manufacturing and designers, before you develop a model, and how you produce results and how you present it to management in a way that they have value and they provide context, so decisions can be made in a more clear and rational manner?
Yeah, it's almost like you have to approach it like developing a requirements base. And that's kind of my systems engineer coming out of me. But as I've gone through, you have fundamental requirements that might be derived from a couple different groups. You might have loads, right, that you're taking as inputs, and really understanding the dispersion of those loads and the discrete application of those loads is super important. That's one. Like you said, the manufacturing, really the tolerancing, the actual like as manufactured state versus as as design state. I mean, they might actually not match, and so you'll have this kind of Venn diagram of oh, this is the design part, but this is actually how we manufactured it because we couldn't get into this area or we had a non-conformance here. So you really understand the as built part versus as designed in that Venn diagram, and that flows into how you're going to model something in a nominal state or in an off nominal state, or modeling the min and max, material conditions. And then lastly, that also drives into manufacturing and really is like the fundamental material properties and where those are from, right? Whether you're basing it on, actuals derived from coupon data, or you're doing it off of MMPDS, A basis or B basis allowables for this type of bar stock or sheet stock. There's all those requirements that flow into just getting started. And in addition, you might have, you might have created it, or you might actually have some kind of CAD that you can start basing stuff off of and doing, mid surfaces and all this stuff. So there's all these things that happen. You have to really, especially for these big projects or complex models, you have to take it almost like a project approach. And it's not just some clear-cut analysis. It's really, you have to do your initial kickoff meetings with the right personnel and really double and triple check your inputs, because sometimes those inputs drive the way you build a model. And if you get them wrong initially, you're going to have to backtrack and basically peel back the code. And it's not like you can just rip it out and slot in something else. So like it's really almost like a project of building a home or something, and touch base with each one of those groups individually, on a consistent basis at first in the project, and then also help hold more of the team meetings where you're basically explaining how you're integrating all these things together to produce a model. And then that's where you're really getting kind of almost like a design review where you're saying, I have enough inputs to create my model now and do these initial studies. And then you come out with another, get together of the broad team where you're showing some preliminary results. And then that helps synthesize into a final discussion of what's the impact, right? And really that's when you're talking to management, you want to produce something that has an impact, whether that's, hey, we get to use this part and as non-conformances, but it's okay for these reasons, or we really have to do a repair, or we have to do a replace, or this allows us to go and test this really expensive part with high confidence, right? Or, hey, we got to work on these loads and maybe we need to scrub our loads because we are predicting that this will break in this test condition. And, it's risky going into the test for X, Y, and Z. That's really what management wants, is they want to have an ability to make an informed decision while understanding, the limitations, of the model. And that's one last thing I would say for FEM is really don't oversell it. It's a very good tool. But if you can combine it with, especially if you're doing testing, some lower level coupon testing, that is using either similar, procedures or similar people and facilities, I think that provides a lot of confidence that you can enter a test successfully. That's kind of what I would say about that, Vinay. I always think of final modeling a little bit like fluid, like CFD. Like it's very useful, but you always want to mistrust it a little bit, and don't oversell it. But use it effectively to make good decisions.
That's amazing, Chad. I really appreciate those insights. As a manager, VP and all that, um, at the higher level, top level, from your vantage point, um, how have you seen finance play a role into the design and development of a product? And how you see that fitting into a test program where it can be used to validate the model, but also find errors in the model? Can you kind of provide the balance between modeling and testing from your vantage point?
Yeah, it goes back to what I was saying, doing the incremental approach. I talked about a couple loads analysis model. In any aerospace program, that's one of the jewels that you will have to continuously create under pressure and polish so that it is really like a very nice, good looking gem at the end. That takes work, and it's years of work. But that really is the fundamental like FEM product that produces the lower level loads with good fidelity to do testing, right? And the end goal there is just, hey, get into a more high fidelity test, or let's say a launch with a launch vehicle, or it could even just be, hey, we want to go around and do flight testing with a fully loaded launch vehicle on the wing of an aircraft. That's what we did at Virgin Orbit. Having that CLA model get developed, over years, you're talking, before we dropped, we were developing that CLA model for a solid, basically 4 years. And that was huge into getting into that thing safely, especially because we had people in the loop, on the aircraft, and doing a good job at predicting the loads of all the various primary structures and even some of the secondary structures. So to do that, you really need the input of all the responsible engineers that are a part of designing something, and them to sit down with the analyst who has really the kind of control and responsibility of the model. And you're just there going through, basically you're looking at 2 other things. You're looking at your CAD model, and you're looking at your detailed final model of that structure being tested. And then you're looking at the CLA model, which is basically a reduced version of your detailed model. And you just have to sit there and just go through everything one by one, all the critical interfaces, all the material thicknesses, and take that kind of detailed, almost like pedigree review approach, where you're checking off all those boxes, for that subcomponent. And then you're like, how is it linked to the forward and aft end? Oh, we're good. Okay. And then you go and meet with them again in 6 months, and you go through the deltas, basically, because you might have some design changes, that might then flow into the CLA model. So that iterative process that you have between a designer or a responsible engineer, which really is everything, and the CLA modeling team or person, is super important. And that's how you get through safe, and successful huge test programs. The other thing that it flows into is the testing of those individual components, because sometimes you can test something as a full scale, sometimes you can't. And most of the times you can't. So you have to test it on a subassembly level or a component level. And for those tests, what you want to see is really good correlation between your detailed model and the test results, whether it's strain gauges or displacements or something else of value. And that really helps you understand whether there are any iterations that you need to make on not only the design, but also maybe on the CLA model, which it feeds into. And that would help with better representations coming out of the CLA model of loads. So there's a lot of this kind of feedback loops within the various levels. And going back down to the fundamental level, which is really looking at CLAs or for like dynamics and loads from that, looking at strength, the strength and capability of certain joints, that's where you start really as the fundamental responsible engineer, and you start doing FEMs, and you do the testing, and you do the building all as one, where you develop a really solid understanding of how these structures fail, basically at these critical joints. And so then you can build that representation of that joint into your higher fidelity model, then do the full scale testing on it, and at the same time understand how those loads in that high fidelity model then translate to the loads in the lower fidelity coupled loads analysis model. So I don't know, Benet, if you've gone through coupled loads analysis in this class, but that's really, if you get part of any project, aerospace specifically, you're going to touch a coupled loads analysis model, really engage, understand it, not only your structure, your portion, but everybody's portion. And if you see anything that's weird or people that are not doing that kind of, feedback loop, call it out, right? Because you want to make sure that if you're a structures person, you want to make sure you're getting good loads from the propulsion CLA engine model, right? If that thing's wrong, you're getting garbage too, and you're testing to garbage loads. So really, there's a kind of a shared responsibility in making sure that the whole entire model is good, even if you're just a part of one of the structures or one of the engines.
That's excellent. So guys, I didn't cover a couple of those analyses, but this is a finite element course. But just to make sure that you guys understand what he's talking about, the launch vehicle is going to undergo vibrations during liftoff, ascent, and so forth. And during those operations, those dynamics can couple with the dynamics of the spacecraft. And so what we want to make sure is both the launch vehicle and spacecraft are safe during all the loading environments you're going to see in service. So that's kind of what big picture that is. You guys kind of looked at that from when I covered dynamics in a very top level view. But that's what he's talking about there on that topic. So Chad, from your vantage point, that's my last question before I turn it over to our team here to ask you questions as well. But from your vantage point, can you explain the benefits of a peer review? Also those that spend time interpreting the results the best they can rather than just showing whatever colorful plots they want to show, because Finite has the ability of showing you some very beautiful colorful plots. So yeah, two questions there. The benefits of peer review. As you know, Chad, you and I never really got a model correctly 100% of the time because it's easy to make mistakes, right? So can you explain the benefits of peer review and the benefits of interpreting results?
Yeah, the peer review is huge. I talked about kind of the paired programming. And whenever you're doing a model, if you can set up that and not do it solo, and that could be someone working directly on the same model as you, and you're kind of in a horse race a little bit, right? They might be taking a different approach and you're really looking at best force wins, or they might be doing another portion of it, right? And they might be doing, let's say, if you're doing a test fixture, they might be doing the test fixture side and you're doing the actual test specimen. That's kind of a good way to split it. And then if you're doing a structure, like a big structure, what's really good is like developing the peer review at your interfaces. So if like I'm doing the LOX tank, maybe you're doing the fuel tank, and then I'm also interstaging with the person on the front end who's doing the interstage. And so we were all three talking to each other. So like interfaces are keys on anything you're doing. If you can pair program it, you're going to be able to find and see things differently than the person that's doing the modeling. And I know that's weird, but like it just happens. Like you can see those in pre and post, and sometimes even in the BDFs, the bulk data files. You could do, for the old school people and doing text editing, and so you can see how things are created, and there's little gaps here and there, because this is all just tweaking a numerical model. It's like CFD, right? CFD is usually, it's a lot of stuff you can't trust. It's a lot better than it was 20 years ago, but it's a lot of little tweaks and you can have a completely different result. Final modeling is not as susceptible to that, but there's little things that can be hiccups in the model that'll either have it crash out or not converge or converge to an incorrect solution, right? That other people can see that you can't see. One thing that I would suggest also with the peer programming is, like, as a peer, have your own list of how you check your model and your best practices, and then you can apply that to someone else's model. And that's an easy way to go and check their model. And usually then you share notes afterwards, and then you make your cross checklist even better the next time around, because you're getting someone else's, their own personal list as well. So that's sometimes like doing 1G load cases, or doing translations. There's a couple different ways to like cross check a model and really ensure it's working correctly. Let's see, presenting results. I like to sleep on results as much as I can. Trying to present them immediately, more than likely you're going to have it wrong. If you think you're right off the bat, just wait a little bit, sleep on it overnight and take a look at it again in the morning. Because sometimes there can be little nuances in the model, and you'll have it mostly correct, but there might be some bad nodes in a certain area, and that doesn't necessarily mean the critical areas of the model and the results that it produces are wrong. But what it does is, if you have these little nuances in the model and you're in a meeting, you're presenting results, what it does is it creates doubt, because there's going to be another person in that meeting that's more experienced than you in FEM modeling, and they're going to be able to see it. You just develop a knack for it, and you can look at the stress gradients or strain gradients, and you're just like, something weird is going on here. And that's why I talked before about doing all those kind of incremental reviews of results, because you can flush out a lot of those things that are within the model. And it might be a little weird area where you're getting some locking, or it's a boundary condition that has 3 degrees of freedom versus 6. But again, it's not polluting the major results of the model, but it is locally like polluting it and causing doubt. So that's what you want to get out of there too. It doesn't have to be a perfect model, but those little inconsistencies will end up tarnishing the reputation of the model, so to speak. So that's why I say, like, be careful about the results, try to sleep on it, get another person's look on it. And that's another thing where you want to compare notes. All post-processing is not created equal. And, you can see that in various programs like the Post and Abacus. You can do different nodal averaging. You can take, maximums. There's a lot of different ways you can skin the cat, so to speak, in post-processing. So if you want to do your best, make sure you understand how your team does it. And some teams can do it differently, but also need to understand what your technical leaders, have seen or want to see as well. Some people want to see kind of the discrete, integration point data. Some people want to see kind of a gradient because everything's really low or really high margin, really low stress or high margin. But when you get into the weeds, especially when you get into areas where there's low margin and you're trying to do a non-conformance, you really want to understand what people want to see, how do they want to see the data, right? And that might be your chief engineer, that might be your manager who's also your technical lead, or that could also be your customer who might have a technical capability as well, and really want to see it in their way. And so that could mean you do it in your way, you plot it in your way, and you also plot it in their way. So you can see the kind of difference between the two, because both are essentially correct. They're just different ways of like I would say, lenses, right? So the post-processing is super important, and just make sure your plots are legible, and you can actually see what part of the structure is, right? If you have a local zoom in of a spot, you might want to have the global view too, with a little circle pointing to where you're zooming into. So that's another thing I've seen is, like, that's for the management, right? That's for management to understand the context of what you're doing. If you're down in the weeds and you're crawling down and looking at each individual blade of grass, you're going to have people's eyes glaze over and they're going to disconnect. So what you want to do is you want to stay high level and create that story and say, hey, I'm doing this turbo machinery housing. This is where it's at. This has a non-conformance in this area. This is a picture of the non-conformance. This is how it's represented in the final model. And you tell that whole story. And the last thing is your results, right? So you really need to not just throw up, the post-processing views, but really tell that story. And that provides the confidence that what you're saying is of value to make agents. So they're my kind of top level suggestions.
Oh, very nice, Chad. Let's just take one or two questions from the audience, and with that, we'll close today. Any questions from the audience? One question from the audience, at least.
Easy crowd today.
Easy crowd. Any questions? Are you guys there? Can we hear you?
What kind of engineer would you kind of qualify yourself as?
Oh, that's a good question. And it's granted, these types can change too. As you gain experience. I have wanted to mature myself kind of as an all around. I would say my two dominant traits are probably designer and politician. But I've heavily trained up my non-dominant, by going, to Virgin Orbit. I mean, 8 years ago, they started with just this idea, and really we had to do everything. And so that's really takes out the hustler side, and you have to do all the design and the analyst and the, politicking. And so those are my primaries. And that's actually why I also, was in aerospace originally, because I wanted to get more into the analysis, and that's really what I did in Aerospace Corporation for 4 years, is really got in-depth into analysis, worked with Finite, and got into all the different pre and post processors, and really used my graduate school knowledge, of fundamental FEM mathematics to really understand what I was doing. So I've looked for opportunities in my career to train up on my weak sides, and I consider myself pretty well-rounded now. So yeah, I mean, I might be right-handed, but I could throw just as hard as with my left hand. And so that was my goal basically. But at heart, I think I would love to be creating art, and doing sculptures or something. I'm a very tactile person. I like to be near hardware, and so I think that's in my blood. But it's definitely merged over the years. I mean, I've been happy with the experiences I've been able to give myself, and I encourage everyone to do that. Look for career paths that put you on the spot, and help develop your non-dominant strengths.
Yeah, Chad. So one question I have for you is, what made you so successful? Such a rapid speed. What will be one characteristic? Don't go too long. Just a quick answer there.
Oh man, I think a top three, I would say, don't take anything too personally. That helps you kind of keep moving on and be resilient. There's a fine balance between saying yes all the time and executing on what is on your plate. And so you just have to walk that tightrope, right? Or that you're walking on the top of a mountain. Each side is like can slow you down, right? You go into saying yes too much, you get bogged down. You go into execution mode too much, you're not going to be able to see opportunities that are coming up in front of you, right? You're going to have your head down. So you have to walk that tightrope. I've been able to do that pretty successfully. And look for a place where you can make an impact, right? That's one of the reasons I went to Virgin Orbit 8 years ago. It's a small team. They're doing something new. And we did it. We were successful on the technical side. The business side, not so much, but technical side, yes. And look for places where you can make an impact, and that will help you grow pretty quickly in your career. And if you're at a place that's larger, that doesn't mean there's not places where you can make an impact. There's always stuff going on. And so just look for those places, whether you were in a company that's larger or, if you're going to a startup, startups are places that you can definitely make an impact pretty quickly, or you can not, and you can be a part of the, the mass of people that get stuff done. So it's, those are the three things I would say.
All right, a final question here from the chat. What is the most important structural test for an orbital launch vehicle? And maybe let's just give the answer within a minute, if you don't mind. So that
The most important structural test, I would say the second stage. I think the second stage is probably the most important structural test. The reason I say that is it's usually if you look at a launch vehicle, right, the first stage is usually like a Mack truck, man. That thing is most of the time overbuilt, and because it has to withstand some pretty punishing loads from the engines, and whether it's reusable or not. That also provides another loading condition that's very interesting. So, first stages in general, they kind of plod along and they get there. Sometimes you have, critical failures but they're more rare. I would say the second stage is probably the most interesting. It's the one that's more like a Ferrari. You're going to have lighter components. It's 1-to-1 on payload. And that's actually where I was playing, as a manager, and designing the second stage for Launcher One. It was really cool because you had a high impact in terms of saving weight, but also you're going to put things more on the edge of the seat, right? In terms of lower margin and using more strain or using more strength capability in the fundamental materials you have in your design. So second stage is interesting too, also because you want to test it as a combined unit, with the LOX and the fuel tank, because it's such a kind of integrated structure, and those tests can sometimes go awry. I mean, those are the ones where you're more likely to fail, and so that's why it's the hardest. The payload adapter fitting and fairing in general, those are pretty straightforward. We did that on my team as well. Had a lot of good success because really it's such a simplistic structure. You're just using hand calcs to design it. That's how we designed it, and then FEM kind of confirmed it, but it was like hand calcs. So the second stage, I think, core is probably the hardest one, the most important.
also, I think engine testing is a very important test.
Oh, that's a given. I didn't count that as structures, but yes, you cannot you will pay dividends always. Every single engine test you do pays dividends tenfold.
I don't think you can analyze your way out of a engine test.
You cannot, whether that's an engine test on the test stand or on the stage test vehicle or on the vibration table. We did all of that at Virgin Orbit. And it was very important to get different results for each one, different boundary conditions for each one. And man, if you do not have all three, you're going to be missing something when you finally go to fly.
Well, Chad, I really want to thank you for spending your time with us. I wish you the best of luck. Thank you for spending time with us. I hope our paths cross soon. And to our audience, thank you for participating. And you have a great rest of your day. Chad, again, thank you for your time. I really appreciate that.
Yeah, no problem. And thanks for having me, everyone. And Vinay has my contact information. If you guys have any questions afterwards, just feel free to shoot me an email at my Gmail, and I'll answer them. I'm all about helping get people in the industry and getting them placed in a good place where they can develop their career. So don't hesitate to reach out. Thank you.
Thank you, Chad. I appreciate that. Thank you.